Fourth paradigm. Okay, so CUDA, we had CuPy, and we had NUMBA, now OpenACC. So this is with higher level language. Well, Python is also higher level language, but with the C, C++, or Fortran. Okay, you can do not with Python. OpenACC is not for Python. So it's for compiler languages. Okay. So here we have a sequential code. I think I have this in my first slide. So these are the books which you may refer to, and this is a website for documentation. Basically, take a sequential code, C, C++, Fortran code. Now it is compiled by the compiler. The compiler converts it to object codes, which runs on CPU, also runs on GPU, CUDA. CUDA compiler converts it to CUDA. Okay, that is not done by GCC, but it is done by NVCC, NVIDIA compiler. There is another famous compiler called Portland compiler. Okay, Portland group, PG Fortran, PGC. So okay, it is not free. I think it's with NVIDIA now, but that's another famous compiler. In any case, so this compiler, NVIDIA compiler, will convert to CUDA also. Now, idea is that I have sequential code. I don't want to worry about all these blocks and threads and so on. I just want to use GPU. Okay, so we can tell the compiler saying, well, this part don't worry. This part is just creating arrays, doing some simple stuff which is not very expensive. Let it be as is. But this loop or very expensive function, I would like it to go to GPU. So what do? I tell the compiler that convert this part to GPU or compile it for GPU. So this is done by something called compiler directive. So this is a direction. This is not a C code like x equal to 5, that is not a C code, it is a directive, it is told to the compiler, okay, do this. Okay. So, I am going to show you some examples, what are the compiler directives, and so most expensive part you tell the compiler that convert it to GPU. So, most of the code is sequential. So, you have sequential code which is structured well. We can clearly say, well, first of all, this code which is expensive code, expensive part of the code, that should not be jumping out, or it should not be using if and if else and so on. Okay, it should be just nice loop or nice vector, nice arrays which can be vectorized. So that part can be converted to GPU. Nobody, when anyone uses gotos, so don't use gotos. Okay, so never use gotos in even sequential codes, and function calling another function, that can be a problem. So function should be self-contained. GPU will be confused if you call some other function. You have to write well in such a way that can be converted to GPU code. So so these are some examples. We have COMSOL. I think well, I don't see it very well. No, this is weather prediction code, not COMSOL. There are some other codes. They are giving you a speed up of, so less than 5% of the code modified. You may not be able to see it properly, but only 95% code is as is. Only some blocks I just said, well, I did not convert it in fact. Well, I did not mean this user did not convert it. It just says, well, compiler do this part. Okay, and it gave a speed up of 9.5, 7.5, 5.5, which is not bad. Okay, I mean 10 times speed up by just putting some few lines in the code is is excellent, right. So, this is power of OpenACC. If you have a nice sequential code, you can just put this one. So, this first thing people advise, you just use OpenACC before going to CUDA. Get used to it. I mean, well, there is no work, well, 1 week of work or not even 1 week of work. If you are expert of OpenACC, you can convert it in 1 day. Now, there are, as I said, there are 2 compilers, Portland Group, and in fact, it gives more options. Portland Group, there is something interesting. So, we will see the compiler directive bit later, okay, in the next slide. So, this codes which have some compiler directives, we can give option to use GPU as well as multi-core. So, it will also convert it to the sequential code. So, it can use only one core, right, but you can tell this compiler to run it on multi-core. So, it will convert it to multi-core without you doing anything. So, this is target architecture. TA is target architecture. So, target architecture can be Tesla, this right now for NVIDIA GPUs, or it could be multi-core. Okay. So, more cores of CPU. So, there are 2 options. So, do not put a bar here. So, either use the first option minus TA Tesla or use minus TA multi-core while compiling. So, we use minus O3 option, no? Remember we are using minus O3 option, minus O option. Similarly, you can use these options while compiling, GCC minus O3 or NVCC minus O3, like that. You can also give more specific option, Tesla CC70. So, these are called computer capability 7.0 is 70. So, this is for some, well, CUDA has been evolving over time. So, some CUDA have some features, some CUDA do not have some features. So, this is right now coded in this, okay. We may not use that option at all, but then you will use whatever CUDA is available, but you can be more specific. I have not done this, I have not tested this option, I have not read more about it. There is another option called unified memory. This is a very strong concept which is not fully developed yet, I would say. Memory of GPU and memory of host can be treated as one memory. So, unified memory, like I discussed, no, Apple's M1 chip, it uses GPU memory and CPU memory as one unified memory. Okay, it has advantage, you do not get lost, I mean, you do not do a lot of copying, okay, and this is for accelerator info. So, I think you no need to worry about this part, it will print some useful information. Okay. This is for Portland compilers, and for GCC we will use this one because GCC is available in Colab. So, minus A OpenACC minus dem geo. So, this one is, it gives you configuration of threads, okay. You can specify configuration of threads, I did not dig into it. This part also I did not dig into it, okay. So, you can offload compiler, but these are options available, you can read. GCC is pretty good manual, okay. So, you can look at GCC options, but these are options available, that is why I put this slide up here. OpenACC is not available with NVCC. It works with Colab, yeah, GCC it works with GCC. It works in Colab, okay. I did check whether it is uploading, it works with GCC. Now, let us look at how we are going to convert it, okay. So, this is my C code, which is adding A plus B to C. Now, this is my library, which is a standard C library. So, everybody is happy with this code, this part. I call a function. So, first I create these arrays A, B, C. By the way, these are called dynamic arrays. I will probably do bit of it on Friday or later. So, what is the difference between dynamic arrays and static arrays? So, these arrays are created, yeah, after compilation, during runtime. Okay. So, here I have specified n right here, but typically n is not specified by the user. I want to run it for 512 cube or 1000 square. So, this is requested during the runtime. So, there is a always you input your parameter in a para file for HPC. So, para file will give you the grid size. So, it is not hard coded right now. Even though I am using dynamic arrays, but I am hard coding it. This n is inside the main, but n is not, if n is not known beforehand, then what do I do? I put this n outside in a para file, and then I say, well, read n and then create this arrays. Okay, so these are dynamic arrays. N is not hard coded inside the code. Presently, though it is dynamic, but n is given inside the function. And again, this is my function. This multiply array. This is my array. Okay. Sorry, this is my function definition. And inside the function, if I ignore this part, it's a int I, then I do a loop. Right, Ci equal to Ai plus Bi. Sequential part. Here I have done one change. Well, two changes. One is this pragma is sitting here, this line, and I put something called restrict. 3 restricts are here. So, this pragma, let us first understand what pragma is. Pragma is called compiler directive. This line is not compiled. Compiler, when it sees the line, says, well, I need to do something. So, what is asking it to be done? So, this ACC is a basically says, well, you need to do something with GPU, okay, that is flag. ACC kernel. Kernel is basically ACC function. You need to create some ACC code. So, copy in. So, which variables or which arrays A and B are to be copied in from host to memory, host to device, sorry, host to device. You don't, you are not, well, I mean, you are telling the compiler saying that A and B will go in the GPU and copy out C, that means C will get out of GPU to host. Okay. So, I want to work with these 3 arrays, but something will go in, something will go out. Okay. So, these operations will be done inside the GPU. Well, A and B are inside GPU, C is also inside GPU, but I am also telling you which will be going in, which will be going out. And the restrict is that is self contained, it does not have pointer floating around. So, for you just think that this is basically a structure which compiler can easily convert to GPU or CUDA code. Yeah. So, restrict, I think you just say that it is make things more efficient. Some things may not work if you do not do properly, but restrict is the pointers are not floating around. So, how do I call it? Call this, how do I run this? By the way, it is, you can see in Colab, it's basically is, well, it's a sequential code, no, without this pragmas and restrict. I just added this stuff and it's ready to go on GPU. So, how do I run it? I just call GCC with -f open ACC, and these are options -o fast. I also use the DUs parallel, and these are okay. So, yeah, so this is DUs parallel, no need to worry, okay, I just copied from example. So, basically you need to use this option -f open ACC, which is available with GCC. Okay, so it's straightforward, no, it's very simple. This is well, I'm just writing something. Kernel operates this function on GPU, copy in, copy from host to GPU, copy out from GPU to host, and a copy from host to GPU, perform action, then copy back to from GPU to host. So, if I say copy list, it's going to do both. So, take the array from host, copy it, then at the end it will send it back. Create list. So, this for working with arrays. allocate memory on GPU, but no copy. So, there is a allocation, delete, deallocate memory on GPU, restrict, pointers are not aliased, hence independence, loop with arrays could be parallelized. Okay. So, this is basically is technical word, but it should be independent, it should not be called from somewhere else, and okay. So, do not make, once you create this array A by pointer, do not manipulate it, do not alias it with some other pointer. I guess everybody understand it, no. So, if I have an array A, I can say B equal to A. So, B is aliased. So, B is a pointer, it is not the full array, but B is a aliased. Okay, now there are some more structures. So, it's straightforward, no, I mean just put few lines and that is it, the code is ready. Of course, for this simple example you do not worry, but for large code it is very useful. So, there are some more constructs. So, there I had pragma ACC kernel. Now, this is very generic, kernel is very generic. I am not telling it, okay, you telling the compiler saying, well, what should you do? So, well, you do whatever you like, but put it on GPU, make it as efficient as possible. But we can be more specific and say, well, so you can tell the compiler that this part of the code should be parallelly executed, means this should happen by various cores simultaneously, various threads. So, loop. So, these are the keywords, okay, parallel, loop. So, parallelize the loop. So, we are telling it. You can combine both in one line. So, I am going to give you some examples, okay, you just wait for a minute. So, this is a command saying that the code below. So, this is going to be working on which part of the code? This pragma. The code inside these two braces. You see the limiting part of a code is braces, right. Functions are within braces, main is within brace. So, this part of the code is to be made parallel, and inside the code there is a loop, and I am saying that this loop should be also made parallel. Now, of course, there is only one loop. So, it is kind of you are giving two orders, you know, is one order is enough, right, as a parallel, and then loop is to be made parallel. So, you can combine into one line. So, pragma ACC parallel loop. Okay. So, this is going to make this loop parallel, means many threads will work on it simultaneously. One more point to keep in mind, that this pragma should be just before for loop. If I put something here, like for example, I may have some sum initialize sum equal to 0, total equal to 0, it will complain. So, whatever you are asking it to do should be just after this pragma, because it does not know, I mean, if you put, let us say, total equal to 0, and this part could have been total plus equal to AI, right. I am adding, this is, it does not like it. You put total here, don't before, for loop should be just below pragma, or this braces should be just below pragma, okay. Nothing in between, nothing should come in between. Computer is still not, well, I do not believe in that is it's artificial intelligence is going to make it, still its programmer tells what to do and is obeying. Maybe it will become more intelligent to take care of this part, but you see, it is very dumb. It does not say, well, no, this is not useful, it is here, it does not think like that. Okay. So, this is, I am just telling you few things we should keep in mind, that if you have various loops, then it should be one after the other, a loop should be separate. So, here I have two pragmas, one pragma and one pragma here. So, imagine that another loop for j, right, this j. So, we say, well, both are loops, why should I create two pragmas? No, I could have removed this pragma and I said, well, there are 2 for loops, it should do it, but there are 2 different loops. So, and it has n elements and it has m elements. Okay. So, not a good idea. So, you use 2 pragmas if that is the case. Reduction. So, you have done reduction before, right, for multi-threading. Why reduction? The reduction is one important thing is to avoid this called cache. 2 variables, 2 guys want to same variable and try to modify. Okay. So, we use lock in multi-threading, but reduction is a good way to get rid of it. Reduction automatically make that lock, that mechanism inbuilt. You just need to add this reduction operator and on which function, okay, on which array or the B will come. Okay. So, let us look at example. So, when I do a loop for example, total or where this one object is to be incremented updated is very useful operation. So, this is matrix multiplication. So, I have 2 arrays A and B, sorry, it is not matrix multiplication. Yeah, so, it is A star B sum of this. Remember sum is has to be done properly. So, I use this parallel pragma ACC parallel copy out sum which is result and reduction plus which variable? Total. Total is to be protected. So, I have total equal to 0, then total plus equal to this thing, and with this within the braces, which brace is it? This one extra brace, yeah. So, this within this brace. So, this part is going to be in parallel with total handled carefully, and after I am done, then sum will be assigned total. Please remember this is a pointer. Okay. So, this pointer is useful. If I do not do it, is going to be problem. It will be called a value and the result will not be sent back. So, I am putting a pointer. So, this is the pointer, and then I am doing inside, but typically should go outside in the main. Well, you can print inside, Colab allows it. Sometimes, well, this will work, this is C code, this will work. So, I think I will stop here with reduction and we will do some more examples after this on Friday. So, any questions on what I did so far? Yeah.
Can we write the parallel loop copy?
Parallel loop, so you mean here parallel loop? I think it should work, I believe it should work. No, I did efficiency wise it do not matter because this anyway is parallel. Sometimes, by the way, it need not be a loop. So, things are to be done in parallel, but not for the loop, then use just parallel, but if you loop, then parallel loop is better. I may have several functions, function 1, function 2, function 3, and they are inside this block. So, they can be done in parallel if they are independent functions.
But maybe we will be using the shared memory, then we can use the loop.
Actually, you do not need to say shared memory. This is with OpenACC, do not do shared memory. You are not, in fact, there may be possibilities, but you are not being asked to do shared memory. That is, well, OpenACC are not great. The comparison is that CUDA can give you speed up of 3000 or so, but OpenACC you will get some 100. Somebody says I can speed it up by 100, I will jump on it. If it is 1 day of work or 1 week of work or even 1 month of work, 100 speed up is great, you save a lot of time, money. OpenACC is not will give you that much speed up on GPU. So, shared memory and all, it may do it, may not do it, that is, it is not very efficient conversion to a very good code, or it does not convert to the best possible code for CUDA.